Another issue that has proven to be somewhat troublesome for many SEEP-W users is exit gradients. SEEP-W computes gradients in elements, both in the x and y directions and the resultant of the x and y gradients. We can view these gradients with the View Results Information command, or we can even contour the gradients. Now, as you likely are all aware, that generally there is a thinking that when seepage comes to the ground surface, there's a criteria that says that the exit gradient should be less than 1. This is a criteria that was developed by Casagrande for flow nets where there is upward flow. We need to be careful, however, with this criteria when interpreting finite element results. Many users have found this quite confusing, and the purpose here is to try and shed a little bit of light on how to use the gradients that are computed by SEEP-W. As I've already noted, SEEP-W will give us the gradients in an element, and then at the element values they are averaged to the nodes for contouring. These are known as Gauss integration regions. In a 4-noded element there are 4 regions. They are really not regions. There is actually a particular Gauss integration point here at a particular value within each element. We compute, or directly from the SEEP solution, we can get the Ix and Iy at each of these Gauss points. When we click in the element, we shade a region, but it's really at a particular point in the element where we compute the gradients. For contouring purposes, we average these Gauss values to the nodes. So if we wanted to know the gradient at this node, we would take this value, this value, this value, and this value, and they would get averaged then to the nodes. And we need to do that for contouring purposes. Let's go to a little bit more detail by opening up GeoStudio and opening up the file in the folder, the Workshop Resources folder under SEEP called Cutoff. Browse and then open the file Cutoff. Click on the All Objects Zoom button and let us zoom into the area on the downstream side just to the right of the concrete wall. For clarity, let us turn off the soil color, and I will zoom in here a wee bit more at where the flow exits the problem. First of all, I should have gone to the results view, and let's turn on the flow vectors, and we can see here that water is flowing upwards toward the surface. Turning off the flow vectors, we can say View Results Information, and we can click in any element and we highlight a Gauss region, which is really a Gauss point, and at each one of these we can then, in actual fact, give you the X gradient and the Y gradient. And then we give you the resultant of the two gradients. Clicking on a node, notice my cursor changes. When I go near a node, I get the average gradient in the y direction here, and at this particular node the gradient is 0.3. I can click right on the surface, and there is a tendency by people to call this the exit gradient. So that shows you how you can get the information about gradients in SEEP-W. You can actually contour the gradients, but I won't take the time to do that here. First of all, in a finite element analysis, the exit gradients, so to speak, the gradients right at the surface here, are a function of element size. The smaller the size of the elements, the higher the gradients. So unfortunately, element size affects the gradients. The smaller the elements, the higher the gradients. And the reason for this is that we are computing the gradients closer and closer and closer to the surface. With a large element, we are computing gradients that are some distance away from the surface. When we are using very tiny elements, then we are computing the gradients closer to the surface, and as we move theoretically toward the surface, the gradient becomes infinitely large. So we have to be cognizant of the fact that gradients at the surface are a function of element size. This does not necessarily mean that we should use very small elements, as I will come back to in a little bit. Also, gradients are a function of geometry. When we have points of discontinuity in our geometry, sharp corners, then we get very, very large gradients. If we smooth out the corner, we get much, much lower gradients. This is because our functions are not continuous at a sharp corner, and as a result we get what is known as a point of numerical singularity, and the gradients tend to become very large. So let's realize that in the field we never have sharp corners, so the SEEP-W computed gradients at sharp corners are not representative of field conditions. Often rounding out the corner makes a vast difference on the computed gradients. It is worthwhile, when we talk about exit gradients, to go back and think a little bit as to how this all started. And when the concept first originated, we were talking in terms of flow nets. And we know that in flow nets we had equal potential drops. But notice that we were taking the gradient over a considerable distance. In this particular case, we were taking the gradient over 3.5 meters, about 10 feet. So back into the context of a SEEP-W analysis, when people started talking about exit gradients, they were talking about an average gradient over a considerable distance. In other words, if we use quite large elements here, we would be closer to what was done with flow nets by taking the exit gradient over quite a large distance. And so from a design point of view, it is better to talk in terms of an average gradient over a considerable distance in the order of meters, rather than looking at the last element just under the ground surface. So think about how this originated in the context of flow nets. Exit gradients were computed and averaged in essence over quite a distance. Exit gradients from a finite element analysis are, as a result, not necessarily representative of field conditions. And so we cannot just blindly use the SEEP-W computed result. We have to apply some judgment to the results. and we need to rethink the criteria somewhat, I believe. And the question isn't necessarily just gradient. It is also specific discharge, or in other words, velocity. For example, if the seepage were so low that the amount of water coming to the surface in essence disappears through evaporation, then even if the gradient was quite high, then it may not be a problem. On the other hand, if the seepage flow rate is high enough so that we can visibly see the flow, then the exit gradient likely would be a problem, and some form of a granular filter protection would likely be required. My point here is that we need to think about more than gradient. We also need to talk about quantity of flow. In essence, at the root of this is effective stress. What we are really saying, that if we want to keep the gradient to 1 or less, what we are really saying is we do not want the effective stress to go to 0. If you take a SEEP-W analysis and you make a column that is 1 meter high, here's a column that is 1 meter high, and you can do this at your leisure sometimes. And if you make the unit weight of water 10 kilonewtons per meter cubed, just for easy comparison, and we say that the unit weight of the soil is 20 kilonewtons per meter cubed, then if we apply a total head, H equal 2 meters here, and H equal 1 meter here, in other words, the pressure is 0, and so to speak, the water table is here. But at the bottom of the column, the water would rise up to here in a standpipe. Then the effective stress, the vertical effective stress, is equal to the unit weight of the soil times the height of the soil minus the unit weight of the water times the height of the water. And so the unit weight of the soil is 20 times a height of 1 minus the unit weight of water times a height of 2 is 20 minus 20 is equal to 0. And as a result, our gradient in the vertical direction is 1. So, stating this another way, that if our vertical gradient approaches 1, what in essence is happening is that our effective stress is going to 0. And having a criteria that says I want an exit gradient that is less than 1, in essence, in a roundabout way, what we are really saying is we do not want the effective stress to go to 0. So in summary, we have to think about more than just gradients. Let me repeat. We have to think about more than just gradients. We also need to think about flow rates, and we need to particularly think about effective stresses. High gradients under high overburden stresses may not be a problem at all. It's only a problem when the effective stress tends toward 0. And there is also obviously the issue of the possibility of particle transport, which relates to grain size distribution and colloidal particles and so forth. So we cannot look at SEEP-W computed gradients in isolation. We cannot simply go to SEEP, say View Results Information, click on an element, say that the gradient is 1 and therefore it's unacceptable. We have to look beyond that and judge the results more carefully than just accepting the computed results blindly, because as we've seen, it could be element size, or it could be the geometry of the problem, All of these things need to be considered.